Jay, thanks so much for joining me on this episode of Concentrating on Chromatography.
My pleasure. It is my pleasure to give some my thoughts.
You spent over 30 years working in ion chromatography. What initially drew you into IC?
Oh, that's a very good question. That brings the memories of my NASA days back because I started as a principal scientist for Mars exploration project for water recovery in zero gravity, and ion chromatography was the main instrument that allows us to do the mass ion balance for anions and cations, and water is very important. So ion chromatography instrument was very well used in this project for, say, looking at micronutrients for agricultural purposes, as well as the purity of the water for astronaut to drink. And that's how I was introduced for 3 years with ion chromatography. Especially, I used Metrohm ion chromatography. And then that leads me into ion chromatography instrumentation and learning more about IC. And Metrum offered me a job to join them 24 years ago, and here I am.
That is great to hear. How has the field of ion chromatography evolved over the course of your career?
Ion chromatography is introduced for water analysis since 1975. It was always used to control the water quality that we drink every day around the globe. And I was introduced, as I mentioned earlier, for anion and cation simple analysis for water analysis at NASA. However, when I joined Metrom, I found a way to look at the ion chromatography can be expanded into various fields of food and beverage or environmental applications, direct and indirect detection of certain ions, and you apply a lot of principles to make the ion chromatography instrument work for you. And most recently, we are having a good success in semiconductor industry and battery recycling and so forth. So over a period of time, I look at the ion chromatography, it just bloomed into many field of applications.
As you might guess on this chromatography podcast, I've spent a lot of time discussing PFAS in general. Was there a specific moment when you realized PFAS would become a dominant analytical challenge?
Let's talk about what are PFAS. Where did it started? So PFAS around the globe is a legacy chemicals that has been used for last 6 decades in the everyday life of a human being, whether you take cooking pans and pots as a non-stick material or AFFF foam for fighting fires, especially wildfires around the globe, and anything that you touch had a PFAS in it. In 2008, a few of my colleagues in India did some work on two PFAS compounds, namely PFOA and PFOS. But it was only using ion chromatography and conductivity detector, where the detection limit was not very great in PPT level or parts per trillion level. However, in 2015, I came across a research paper and a method developed in Sweden using combustion ion chromatography as a technique to look at the holistic approach of total fluorine analysis. And that intrigued me. And then I was blessed to have working with researchers at Clarkson University and Harvard University, renowned universities doing these early days of PFAS research. And especially their focus was on AFFF foam, which is a firefighting foam that is being used around the globe. And that was a turning point of PFAS analysis, bringing into the limelight, into the mainstream of analytical instrumentation.
We often hear about targeted PFAS analysis, but what is AOF, absorbable organic fluorine, and how is it different?
So there are thousands and thousands of chemical formations that has been into the environment, and we contaminated the environment. That's how I would look at it. When you try to now remove or destruct the PFAS, it also forms different kinds of PFAS compounds. Now, permutation combination looks at like more than 10,000 compounds. So when you look at targeted analysis, we are looking at maybe 40 or 100 PFAS compounds. So when you look at that compounds list, you are looking at less than 1% or less than 2% at the max of the total PFAS compounds in the environment. So that's a targeted analysis where specifically it is sensitive, it's selective, and it is very useful instrumentation to give you specific information of that compounds. Okay. Now, when you look at the total PFAS compounds, the holistic approach is to look at total organic fluorine compounds in the environment. Okay, and that's where the AOF method or combustion ion chromatography method gives you the total holistic approach of total fluorine in the environment. And adsorbable organic fluorine is the very small subset of the organic fluorine or total fluorine umbrella. However, it is a very complementary technique to the LC-MS-MS.
Yeah, and I'd really love to learn more regarding what are the limitations of targeted LCMSMS and how does AOF help address those limitations?
Yeah, as I mentioned earlier, targeted compounds, we can look at only 40 to 100 compounds by the LC-MS-MS at the max because any chromatography instrument cannot isolate or separate more than certain compounds at a time in a given period of time in the chromatography run. So in that case, you have to also look at ionic suppression in the LC-MS-MS, which is matrix dependent. And then in those cases, you have to use internal standards. So isotope label compounds to be used for targeted analysis is also very limited. And in that case, also it's very expensive because to make the isotope label compounds is also very expensive. So expensive proposition to look at only less than 2% of PFAS compounds, it's a good technique, but that's the start. Now, when we look at the AOF as a combustion ion chromatography, it does not discriminate between any class of compounds. It is just basically an instrument that breaks the carbon fluoride covalent bond to give you a fluoride ion that is detected at a very low level by ion chromatography. So that is you ask about the limitations on the LC-MS-MS is about the cost and the number of compounds versus on the combustion ion chromatography, the most limitation is you look at the total fluorine compounds that includes inorganic fluorine and organic fluorine as well. So looking at those techniques, those are the limitations of both techniques.
One of the reasons I was very excited to speak with you today, Jay, was that we really haven't covered combustion ion chromatography on this podcast all that much. Can you walk us through how CIC works for AOF determination?
Yeah, sure. I'll try to explain you as much as I can in very layman terms. So this is a reincarnation of the TOX analyzer. So for many, many decades, scientists has always used total organic halogen analyzer, and it is mainly used in petroleum industry to look at the halogens in crude oil and halogens in various petroleum products, where people were burn the compounds and release the organohalogen compounds, including like chlorine, fluorine, bromine, and iodine, collect it into a vessel and then titrate or microcoulometer titration or argentometric titration will happen to look at TOX analyzer. taking that technique and putting ion chromatography as a detector gives you sensitivity and selectivity for each halogen that you are looking at. Okay, so basically you are taking the sample and you are burning at 1000 plus degrees centigrade temperature where the carbon halogen, or in this case, carbon fluoride covalent bond is broken. And then you collect the fluoride ion and then you do the ion analysis on IC.
And I believe you just alluded to this, but what makes CIC particularly well suited for total fluorine analysis?
Yes. So in the name of the game here is the efficiency. You want to have an instrument that gives you the best efficiency of combustion, means that it is efficiently burning and breaking the carbon fluoride bonds to give you a total fluorine number. So you introduced amount of oxygen, which is a fuel gas. You have an argon as a carrier gas that brings the ions into the absorption solution. And at the same time, you are timing your sample introduction into the hot zone or hot oven in a very timely fashion and efficient fashion to burn everything that you put in. And that's how the combustion IC makes a very suitable instrument for total fluorine analysis. Here, bear in mind that it also decomposes any inorganic fluoride compound like sodium fluoride, any fluoride salt will be also decomposed, and you also gonna get the fluoride ion as well.
I spend a lot of my time helping labs solve their sample preparation challenges ahead of chromatography. What specific sample prep challenges exist with this approach?
The biggest challenge for, say, adsorbable organic fluorine or a total fluorine with a combustion IC, interference of inorganic fluoride. So basically in US, that is a bigger challenge because in US, all drinking water is fluorinated. So when you add inorganic fluoride to the water for drinking, it ends up in your wastewater. So that inorganic fluoride, think about anywhere by regulation, anywhere between zero point 0.5 ppm to 4 ppm is required. So just give you an example. Let's take a one number and say 1 ppm of inorganic fluoride in is in every tap water in US. Okay, so that's a 1000 ppb of inorganic fluoride. In that matrix, you are trying to achieve less than 5 ppb or 2 ppb of organic fluorine analysis. So that is a limitation for sample preparation, that if you do not select the sample preparation material and the technique to eliminate that inorganic fluoride, then you are going to run into a lot of background fluoride. Now, to add on to top of that is a fluoride background from the environment. Say, for example, air conditioning vents. They also have a picogram level of fluoride coming due to the refrigerants and the gases that we use for refrigeration. Okay. And so that also makes it difficult to get an inorganic fluoride background in your combustion ion chromatography. On a sample preparation side, you look at the carbon material. That carbon material, if it's not selected properly, that may have a very high fluoride background as well. So it's a lot of points on the interference check, and these were the aspects that was considered and very carefully evaluated during the making of the EPA method 1621.
Yeah, and how I understood it was that you were directly involved in developing EPA 1621 along with ISO 18127. Can you walk us through how a method like this actually becomes a standard?
I would say that first of all, I will correct myself that I was directly involved, but it is a group of brilliant scientists from the industry that worked together through the grapevine of ASTM D19 and DIN in Germany that developed this method as side by side, working together and making this method possible. Of course, as I mentioned earlier, since 2015, this work started in Europe, in Sweden. Then it got into the regulatory arena in Germany as a DIN, and then that DIN method got approved, went into the ISO stage, and then that DIN method got adapted through the collaborative effort with ASTM D19 and US EPA. So from 2015 to 2020, this was the 5 years of a lot of discussions and a lot of brain browsing that happens during the entire method development.
With so many people and organizations involved, it would seem like there would be a challenge in getting a consensus. What were the biggest challenges in getting a consensus across stakeholders?
First of all, we as a scientist love to discuss science, regardless of which badge or whom you are working for. So in that case, if you put your ego aside and work side by side, wonderful things happens. And this is one of the wonderful things that think about government agency or government people seeking the help from the industry and the industry participating in the science and the development of the method that benefits the entire global community. And laboratory community, vendor community, and the government officers all came together to work together. And that's how we had making of the method. However, there were always debates, hard discussions that do happen. But by end of the day, when you do the experiment and then the data speaks for itself.
Well, I'm certainly very fortunate that chemists and scientists enjoy talking about their work and the science in general because that's really what makes the podcast possible. How do you balance scientific rigor, let's say, with practical usability in a real world lab setting?
It is very scary, when you are trying to develop something new in the industry. A lot of people will get scared, like, oh my God, government is getting involved. So now they're going to come after me with a big stick of fines and a lot of regulations. So that is the balance that you have to find out. And then once you get the people convinced that, yeah, this is purely science and it's good for the humankind around the globe, and then everything works out fine. But it is a challenge to keep the scientific hat and the scary hat together.
I can imagine. How are regulatory frameworks evolving around PFAS, especially beyond drinking water?
You know, I would say government and scientific community around the globe is 100% aligned, no matter what language you speak, but they are fully aligned to look at these compounds of PFAS as a health hazard to the human being or for future generations. And in that case, they have a very brilliant strategy that is developed. Like, first of all, let's cut the production and the use of PFAS compounds. That's the first step. Second step is to reduce or eliminate from the environment. And let's start with the dirty metrics like wastewater first, and then move into clean water like drinking water. Now, what makes the wastewater dirty means not only the cutting the use, but also the leaching of the Superfund sites or these many decades of dumping of waste products into the landfills that leaches into groundwater, comes into your drinking water as well. So all these aspects is been looked into as a regulatory framework. Of course, it takes years and years to develop something policy wise, dependent on who takes the administration and who drives the regulations. So that is sometimes it may become like a political issue, but regardless, when everybody is aligned, it always moves forward.
You mentioned textiles and food packaging becoming areas of focus. What's driving the interest in those areas?
Well, I would say that as a human being, especially around the globe, we are so much spoiled about using single-use containers. Take an example of a coffee cup. Every morning, somebody wants to have a cup of coffee to go, and we take this coffee cup and we have enjoy our coffee and throw it into the garbage can. Now, we have not thought for so many years that this coffee cup were coated sometimes with the fluorinated compounds to keep this thing warmer enough for longer time or to not get your coffee cup soggy so that it does not collapse while you are drinking hot beverage. So those were the things ended up into garbage. At the same time, we enjoyed our fabric in our car, but we don't want to get it dirty, so we always had a water resistant spray on those things, namely Scotch Guard, right? So those automobile fabrics, our ski gears, water repellent raincoats, and fabrics ends up into somehow into landfills. And that's where to cut down, we want to make sure that we don't use these PFAS compounds in this type of products to begin with, and over year of that practice will make the PFAS contamination lesser and lesser throughout the years.
Do you see AOF becoming a regulatory requirement, or is it more of a screening tool?
I would suspect, I cannot speak for government policies, how they are going to form, but I suspect that it will start as a screening tool to begin with to look at the gross contaminations of these PFAS compounds or total fluorine compounds in the environment. And then it will propagate into a regulatory framework of regulation, like in US, it's called NPDES permitting for wastewater effluent after treatment. So it will become a regulatory method eventually, but of course it will start with a screening tool to just assess first, like how much contamination we are having. In my last 3 to 4 years of experience with 1621, we have seen laboratories reporting target versus AOF numbers more than 300 to 4,000 fold difference in total fluorine mass balance.
That's a pretty eye-popping number, I would say.
It is 1%, 2% versus dark PFAS compounds at 98%.
And I know you've also worked extensively with ICMS, ICMS, MS. Where do you see these techniques fitting into PFAS analysis today and moving forward?
Yeah, so ion chromatography always looks at the small molecules, ionized compounds, and this in the world of PFAS. And when we are trying to remediate the PFAS compounds, we form the smallest PFAS molecule that is water soluble, namely trifluoroacetic acid or TFA, and difluoroacetic acid as a DFA. So those molecules cannot be get captured on the carbon material AOF because they are hydrophilic in nature. So when you run the water through that carbon material, it always falls out. You cannot capture it. You cannot capture TFA 100% on the carbon material to get an assessment. So in those cases, ion chromatography direct injection method will definitely help to achieve separation of these compounds with common anions in the water. At the same time, help of mass spec gives you sensitivity and selectivity of this compound detection. So as a matter of fact, there is a ISO method on the horizon using ICMS-MS or LC-MS-MS for TFA analysis. When you mentioned about the polar chemicals, I was going to sidetrack you a little bit. That use of IC and the ICMS-MS can be also helpful to look at polar pesticides like glyphosate and glufosinate and so forth.
Do you see a convergence between total fluorine methods and high res mass spec workflows?
Total fluorine method, looking at the combustion ion chromatography, that would be like I would say, holistic approach of looking at total fluorine, where high resolution mass specs are going to be looked at pretreatment of the compounds that you are supposed to break them into smaller molecules. So, for example, if you take PFAS compounds in C13, C14 range or carbon 13, carbon 14 range, you want to break down that into C4s and C8s by some kind of like sample pretreatment, hydrolysis, high temperature hydrolysis, and so forth. And then you try to extract that and run it into the high-res mass spec for looking at those compounds. So these are all techniques that works, but 100% I'm convinced that combustion and chromatography will give you a gross estimation of total fluorine 100%.
One question I always like to ask, was there anything we missed, Jay, regarding ion chromatography or any of the PFAS developments that you've seen as of late?
Using the combustion and chromatography, AOF method is just a beginning. Now, as we start going into lower and lower detection limits, then you have to also look at the sample preparation techniques that allows you to achieve lower detection limits. For example, Metrohm combustion IC is right now with the current setup can get down to zero point 0.5 ppb detection limit. So in other words, 500 parts per trillion, we are right there. Now, if we improve the sample preparation, volume, technique, and background, inorganic fluoride background mitigation, which will allow you to go even below 100 parts per trillion or 50 parts per trillion. I'm convinced that it is not that far away. And on top of it, if you take the extractable organic fluorine method, which is very good sample preparation technique for LCMS-MS, used under 1633 method or ASTM 8421 method or drinking water methods 537 and so forth. So all these technique, if you combine and improve on that, you can also do the extractable organic fluorine sample through the CIC for screening as well before you put it on your LCMS-MS.
Well, this has been super educational, super useful, and really provides another dimension to the PFAS conversation that we've continued to have on the podcast. Jay, thank you so much for your time today. It was really great talking to you.
It's my pleasure, David, to meet you, but hopefully in future we will cross paths and it will be my pleasure meeting you.
Absolutely. Thank you so much, Jay.
Thank you.